So today's speaker is Rob Pfaff. He's a space scientist in the Space Weather Laboratory at NASA Goddard. And he did his PhD at Cornell University in 1985. And after that, he joined NASA as the leader of the electric field investigation team. And his expertise is developing in situ experiments for satellites and also sounding rockets, and also ionosphere electrodynamics. Most recently, he was a PI of the Vector Electric Field Investigation on the CNOS satellite, which is what he will talk about today. And he, I think, also will give a seminar tomorrow at SWPC, if anyone is interested, on a different topic, I think.
Right, on our rocket measurements. Okay, great. Thank you very much. And I must say, it's a real pleasure to be here. I should point out that I feel coming to Boulder is really like coming to Mecca for when it comes to the upper atmosphere and the work done here at NOAA and of course at University of Colorado Labs. It's really a great pleasure and privilege to be here. So I'm going to talk about results from CNOS. And for those of you who had heard my talks before, if you're expecting a long talk with lots of data examples, you will not be disappointed. And my goal here, I think, is just to share some of the really great results we're getting with CNOS, and I'm sort of just going to show a lot of the nuggets or CNOS greatest hits or something. But these are really just from our experiment, the electric and magnetic field experiment. So here's a picture of CNOS. It was an Air Force mission. It's not a NASA mission. It's very important. As the Air Force commissioned CNOS as a space weather probe to understand irregularities and be able to predict them. It was launched on April 17, 2008 into a highly elliptical orbit with a 13-degree inclination, and subsequently it re-entered about 7.5 years later. So one of the great things about CNOS is we're able to get continuous measurements for over 7 years. Here's a picture of CNOS inside its Pegasus fairing. So you can see it was what we call a small satellite now in today's age. Small satellites, CubeSats, are much smaller, but this is basically about 1 meter across, and it's again in the category of what we call small satellite. NASA has like a small Explorer program. Pfaff was like this, fits inside a Pegasus. The actual mission profile, again, we launched here in 2008 into this orbit, and we launched into one of the lowest solar minimums ever recorded. I know everyone in this room knows all about that. And but eventually, activity picked up, as shown here in the timed EUV data. And as it did, it sort of accelerated the orbit decay. The apogee is always what comes down first. Perigee usually just until it stays about the same, and then at the end it circularizes, and then you have a very sudden, relatively re-entry. But basically, we have data for this entire period. There was a period about 3 months, which was called the hiatus, when we ran out of funding for operations. We put it in the safe hold, and eventually we convinced the powers that be at AFRL to keep us going, arguing that the best was yet to come. And indeed, for much of the science that we were interested in, the lowest altitudes, really at 400, 350 kilometers down below the F-peak, or at the F-peak, as I'll be showing in the talk, is some of the most exciting. The instruments on CNOS are shown here. AFRL provided a Langmuir probe. NASA funded Rod Helus through what we call the Mission of Opportunity program, with a neutral wind meter and ion velocity meter. It's called the CINDY package, very successful. I'm actually a project scientist on CINDY. Usually I'm standing up talking all about CINDY, but in this case, today I'm going to talk about VFI, the Vector Electric Field Investigation, for which I was the PI on, but I was funded entirely by the Air Force. There was no NASA involvement whatsoever. And we provided DC and AC electric fields, a magnetometer from Maricunha, our own Langmuir probe, which was in a fast mode, and a lightning detector that came from Bob Holsworth at University of Washington. There's also a GPS receiver from Paul Strauss at Aerospace, and Paul Bernhardt had his beacon on this satellite that was called Certo. So these are the experiments that we built and that I'm going to be talking about today. Here's just a picture of the hardware, just to show you that we built this all in the lab. The 6 booms, they were 10 meters long each to give us 20 meters tip to tip, preamps, Langmuir probe, lightning detector, main electronics, but with a burst memory, and this is the magnetometer. So they all fit on the satellite. I'm happy to share all this later, if anyone wants the slides. But basically, we had one electronics, one instrument, but with many sensors. They were all controlled in one spot, so the burst memory. I really learned all this from Chuck Carlson on Pfaff, that you really have one central location to capture high speed and high time resolution data. So, what do we want to talk about today? Well, usually you pick one topic and you focus on it. As I said earlier, that's not going to be the strategy here. I want to give you some of the highlights from the electric field experiment and plasma densities, and I'm going to be talking mostly about some of how our data contributes to the question of spread F and how is that formed. Going to show some magnetometer results, both DST observations from Guan Li and some of the current measurements, and then I'm going to end with some of the wave measurements, and we're really tremendous wave data from ULF to HF, but I'm going to be focusing on some of the ELF, VLF measurements. Now, just set the scene. I know everyone in the room knows this, but nevertheless, it's worthwhile to show. Here's our ionosphere, a model from the IRI, sort of looking down on the Earth. So this is at the equator. But basically, this is 2,000 kilometers. The basic ionosphere is shown in red on the day side, and then, of course, it extends around the night side. But basically, this gap, as you know, the F region, E region kind of disappears due to recombination, and we get the F region ledge is around 300 or 400 kilometers on the night side. And that's a particular interest to us and to this talk, because that's where the large-scale instabilities are formed. And for those of you who have, I'm sure you can't avoid it, one of the big science questions at the equator is, why does it become unstable at night? And again, I could give a whole talk on this, but basically just to set the scene, many different ground-based experiments. I'm particularly I want to highlight the ones that Hika Markov, just for decades have shown that at nighttime, at sunset, the ionosphere becomes unstable. And they, for example, with the radar, they look straight up, they get the backscatter back, and you plot that altitude versus time, you get what's called a range time intensity plot, or RTI. And as you can see here, this is irregularities. Is believed to be on the bottom side of the F region at night, the bottom side of the ionosphere. It moves upward. You get this instability. This is called plumes. There's a whole studies on this. And you also get some E region irregularities. And the question is, this turbulence essentially affects navigation and communication signals. It is the reason CNOS was flown, was to try to be able to not so much characterize this, although we do that with the instruments, but really to understand it and understand why it happens, and then could you model this and predict it? So basically, in a nutshell, this is a fairly big event. You get small events and even larger events. I'll just show a few examples. I'll just point out it's a long-standing enigma for decades. Here's one without any high altitude plumes. Here's where the F peak was down at around 300 kilometers, just to sort of show one that's not as spectacular. Where you're seeing this black, that's the sort of the backscatter power. Here's another rather famous one that Mike Kelly published. I'm actually going to come back to this later, but I like this to emphasize it's a large-scale, planetary scale phenomenon. It's not just something very local, just overhead. Of course, the radar works as a pinhole camera. It's just looking straight up, so you don't really know how it's evolved, but you can make assumptions, and from those assumptions get a sense for the large. This is 1,000 kilometers and that sort of thing. And you can also see how it starts right after sunset. Come back to that. Then, just as you think this is the biggest one you're ever going to see, Ron Woodman published this one that was associated with a magnetic storm, which actually went past the upper range gates. And you can see that this phenomenon, and you can imagine, if you have GPS or something, you totally lose lock due to the scintillations, and it's a major space weather problem. Well, we know actually quite a bit about spread F already. And just to highlight what we learned from some past measurements with satellites, this is the Bill Hansen's data from the AE satellite in a paper published by Roland Sonoda. This happened to be radar measurements from quadrants, so here's this black backscatter. Through that backscatter the satellite goes. This is what the satellite measures along this track, the red line here, with just the plasma density. And you can see what we call these depletions, huge depletions, orders of magnitude, and the deepest ones are associated with the strongest backscatter. Here's another one. This is from a rocket measurement called Plumets. We were involved in at Cornell, my advisor Mike Kelly. And as you can see, here's the radar track, and as we go through these areas of irregularities, this is what the rocket measures. Again, you see the big plasma depletions. So what does CNOPS measure? CNOPS, we have, 40,000 orbits, whatever. We encounter spread F frequently. It's, you can do statistics. I'm not going to be showing you those, the seasonal, longitude, everything. But actually, when we first launched, we were surprised to see so much spread F, not at sunset, but later after midnight. It still is an enigma. Of course, the spread F could be born here and propagate upward as it rises. But nevertheless, here's an example of some of the CNOPS data. And I'm going to be showing a lot of data in the same format, so I'm just going to spend a minute orientating that right now. The bottom panel is the information about where was CNOPS, where this data was gathered. And essentially, the black line is this track, longitude, latitude. The red line is the altitude, so perigee was right here, for example, at 400, and apogee was on the day side in this case. The red line is just placed as where's the magnetic equator. And again, CNOPS had an inclination of 13 degrees, so even though the plot goes to plus or minus 25, the black line only goes plus or minus 13. So what you're looking at here is the bottom panel is the density from the Langmuir probe. Then we have the electric fields, the DC electric fields. We subtract V cross B, we rotate it into geomagnetic coordinates, so we have a zonal component, which is positive east, and we have a meridional component, which is positive, essentially up or out. And in fact, just to spend a minute, and then the top panel is the E cross B vector arrows associated with these E fields. So right away you can see that, there's some standard things, that the direction of the ambient electric field and hence the plasma drifts change between day and night, and as you can see here from the arrows. And that inside these plasma depletions, the E fields get stronger, and they're generally upward and westward. Now I'm going to blow this region up. This is actually, I think it was the next orbit, but nevertheless. I'm now going to show a sort of an enlargement in the high time resolution data from the instrument. Essentially what we're looking at here is 6 minutes of data. And in the bottom is the plasma density depletions. So these are these big depletions, orders of magnitude, getting down to below 10 to the 2, seen here. And then here are the associated electric fields. And what you see is that what the electric fields are is that there's a very strong polarization field, an eastward polarization field within the depletions. And what's amazing to me is how well the electric field, zonal electric field, correlates with the log of the ion density. I mean, it just almost tracks it. It does track it. You have 2 completely different measurements. So this is the polarization field associated with the depletion. And again, an eastward field, if you go through the geometry, is going to be a rising upward plasma motion. So these are the electric fields associated with the rising depletions or bubbles. There's also a meridional field, which is essentially outward. That's associated with a westward tilt. All of this is not new in a sense, but it's I think demonstrates what we're able to measure with the VFI instrument. And here are the irregularities. So the same instrument that gives you the DC electric fields also gives you the waves. And here from the ELF data, you can see the strong irregularities. So these are what correspond to what gives the backscatter for the radar and what contributes to the navigation outages.
Yeah. Question. So the E cross B drift is then in meters per second?
Yeah, meters per second.
And
Yes.
Is that an actual motion?
Yeah, the plasma is actually moving. Yeah.
It is a motion.
Relative to the background. Yeah. there's a small drift here, which you really can't see on this scale of a fraction of a millivolt. So that's the ambient drift, and then these depletions are actually moving. I just want to point out that this correlation, or if you call it that, this relation is a correlation, but it's stronger. I think there's definitely a causality, obviously, between the E fields and density, is not new. That has been is an outgrowth of the Rayleigh-Taylor instability to explain this. This is the simple linear theory showing how the density and the zonal electric field are correlated. This is from a paper by HAO and NCAR, and Tom Magson also showed this with San Marco data. So the Rayleigh-Taylor instability is sort of what we all turn to explain spread F. It's an instability where you have a heavy fluid over a light fluid. You have magnetic field lines sort of coming out of the board, out of the slide here. They have a perturbation electric fields, which then grow. You can go through the geometry. And that's sort of how we all tend to think of this. These are these rising depletions, right? These rising instabilities. And then they then cascade to smaller irregularities. Here's the growth rate. You can see how it depends on the eastward electric field, the wind, the collision frequency, so it's height independent. And I think in general, this works. We just showed you with the previous slide, that this seems to hold together quite nicely. But the problem is, it's not the whole story. And the question, should we declare victory? And this was the words of Michael Mandela, who at one ISEA meeting just said, declare victory. I remember when he said that very strongly. But the question is, there's two problems. One is, this heavy fluid over the light fluid happens every single night at the equator. So every night we should get this. Well, you need something to start it. People talk about gravity waves, which is an excellent candidate, or some other perturbation. But nevertheless, it doesn't happen every night. And it's quite seasonal, it's longitude dependent. And also, a more difficult problem is it's a slower instability. And when we see spread F sort of snap on at the beginning, it's hard to use the Rayleigh-Taylor instability for its onset. But it works very well for the evolving depletions. So what I'd now like to do is show you some 1 month of continuous density data from our experiment, from CNOS, because I want to sort of emphasize that we have the continuous measurements, but also how they seem to vary, they do vary significantly from, within just 1 day. 1 day would be 15 orbits. Again, here is the black is the footprint, the red is the altitude. And you can see sometimes you get nothing, sometimes you get these big sort of bite outs or whatever, cavities. I'm going to talk about those. And all these sort of wiggles here, that's the spread up. But you can just see how variable it is from day to day. Orbit, these are all 90 seconds apart, and yet it's continuous. And that's one of the beauties of CNOS, is you can actually gather the data and do a tremendous job with the statistics and really understand what's going on. And previously, we didn't have that luxury, at least not with NASA missions such as AE or DE. So now I'm going to take four consecutive panels. And I'm not going to call this a depletion. I'm going to call this a cavity. It's much bigger than these little lines here are the spread F depletions. And what you see here is 4 consecutive ones, 90 minutes apart, all show this big cavity, all in the same, roughly, longitude sector. Whereas I'm going to go the same day and look at 4 consecutive ones later, and this is part of the movie I just showed you. You don't see anything. So what's going on? Well, we don't really know. But we do know that those cavities were times when, not when you had a depletion, but when the ionosphere rose above the CNOS orbit. So it appeared to be a depletion, but in reality, it appeared to be the ionosphere went away. In reality, it just rose above CNOS. And this is from Jeff Clensing put this together from the, I think the SAMI 2 model. But whatever, here's the actual ionospheric peak. And so here CNOS goes below, and you can actually see, that's when you have a depletion, a cavity. Get mixed up here. Now I'm going to put 4 of these same ones together. I'm going to plot them all at the same longitude. And as you can see, they don't line up in longitude. Instead, they're controlled by the local time. And this black bar is the eclipse bar. I should have pointed that out earlier. The black bar is from daylight, sun and darkness. And so here's sunset. And you can see that they're controlled by the actual setting of the sun. And consistently, when you see the ionosphere going up, it happens right at sunset. And there's a reason for that. There's a large, what we call pre-reversal electric field, a large zonal electric field, which makes the ionosphere rise right at sunset at the equator. Here's a few other examples. These are consecutive orbits, all plotted in the same longitude. And you can see this sort of cavity tracks sunset. It doesn't track necessarily the longitude, if you were like thinking of tides or something. Now, tides can be involved, but the actual controlling factor is the local time. Here's another one, and then here's another one. So again, this is a time when the ionosphere just gone above CNOS. Now I'm going to take all the data from that movie, and I'm going to put them together in a plot in which all the orbits are now shown lined up next to each other. Each line here is 90 minutes apart, and you're plotting local time, so noon is in the middle. And here's the sunset feature we've just been looking at right up here. So this is plasma density. This dashed line refers to the perigee of the satellite, so about in this case, 381 kilometers. There's so many things to talk about here, but I want to just emphasize that where it goes black, those are cases in which we saw the cavity, in which the ionosphere rose above CNOS. And we're getting this just from the density data, which is a scalar. We're not using any attitude or anything. We're just lining up these continuous measurements of the plasma density next to each other. And you can see right at sunset, they rise. Now, what's interesting is they're very confined in longitude. They don't, it's not like the whole, there's certain longitudes where you get spread out and certain ones that you don't. And not only are they very confined in longitude, they're again controlled by the local time, which in this case is around 1900. Now, there's not that much data, but we can still make a plot of just taking that same data and now local time versus longitude. And you can say for this particular case, again, here you can actually see that these were the preferred longitudes in this case. But they are sort of spread out, and as I showed earlier, they can be, they're clumped together. Here's another one from November. Again, you can see this is where they went below. And then here, in this case, it's more over the African sector. So what's going on? Well, the most important thing is to look at the electric fields. And the electric fields are shown here. And in the top panel, we show the E cross B drifts that are upward. And in this panel, we show the E cross B drifts that are zonal, or east-west. In this case, I'm just focusing on three different orbits. Again, this is where the satellite was. This black means it's in eclipse, so it's right at sunset here. Here are the large cavities. And the first thing you see is that this is this pre-reversal enhancement. That the daytime electric field drifts are very weak, but right at sunset, they get strong. And when they get strong, the ionosphere rises. And then it changes direction, so why we call it pre-reversal. But the zonal drift is what I want to emphasize now for the remainder of the talk. Because you can see here, the drifts are westward, then they shift to eastward, which is the regular nighttime direction. But wait, when it goes below the ionosphere, below the F peak, it shifts direction. It goes back to westward again. See that here and here. And I'll show you a few other examples. These are now just the zonal drifts. What you can see is every time we go below the F peak, the direction of the zonal field has changed. The zonal drift has changed. There's still another one. And we think this is very important for the physics of the onset of the spread after instability. Let me show you here. Here's that same plot again versus local time, where I plotted every single orbit next to each other on a color plot. Here are the cavities, and here are the associated zonal drifts with them. So the deeper ones seem to have stronger zonal drifts, but it's uncanny that it seems to be every case. Here's another one in November. It seems to be a regular feature of the ionosphere. And I was all prepared to say this isn't any model, except Art Richmond told me this morning that it was in his model. So, but nevertheless, people like Joe Huber and other modelers who look at the low-latitude ionosphere to predict, when are you going to have instabilities, don't, to my knowledge, do not have this shear case. Now, why is the shear important? Well, the shear is important because that's a source of free energy that can drive the region unstable, and we like to suggest that maybe some sort of Kelvin-Helmholtz instability associated with this shear might create these large-scale waves. Now, one very important feature of spread-F that I didn't point out was it seems to be governed, or seems to portray periodic spacings. This is an example from high in the ionosphere. This is over 600 kilometers, and there's here are spacings that are about 500 kilometers between them at a very high altitude. And it's not uncommon. It's got to be a clue to what's going on. Whatever's creating the spread F just can't be some random stochastic process where you get some spread F here, some spread F there, but there's some sort of orderly input or driving force. But now when we look at the lower altitudes, here's our cavity that we've been talking about. I'm going to suggest that these, what I call undulations, and it's the same relative spacing here than here, are actually or possibly due to this shear instability. In this case, as in all cases, they're very clean on the day side, so there's some primordial instability that's formed, and then they evolve on the night side as the sun goes away and the polarization fields within the bubbles can get stronger. So again, we had shear, we had the pre-reversal enhancement, and that we suggest is driving it unstable. So now here's just several examples. It's very common. You see these large-scale instabilities, always cleaner on the day side. And we're trying to relate those to the shear right now, and it's the shear as far as quantitatively. But you can see you get some very small ones at the beginning. And the whole idea is, again, this sort of shear in the zonal flow right at the F region ledge, create these, what I call undulations, and they themselves then evolve very quickly into these spread F depletions, and that's where the Rayleigh-Taylor would sort of take off, or take over. And there's been quite a bit of theory work on this by Heisel and Kudecki and others, and Kudecki himself in another paper showing that something like this at the bottom side is actually driving spread F. And but Dave Heisel has some rockets from Kwajalein, which I think show this definitively. Kudecki also has a rocket and showing the shear. And I think this is sort of a very important piece of the puzzle, which we haven't appreciated because we just didn't get down low enough. I think we're used to at high latitudes where the magnetic field lines are vertical, that if we took data at 800 kilometers, that's the electrodynamics. But at the low latitudes where the magnetic field lines are horizontal, we really want to think about the fact that the fields don't map, and there's no reason to expect the fields, say at 300 kilometers, are going to be the same at 500 kilometers. Now, getting back to the Kelvin-Helmholtz instability, I remind you all that this is a very common instability in nature. You see it on Jupiter and this and that, but I thought I'd just show some slides here. This one is actually from NOAA, of evidence in clouds. And my favorite example is shown right here. This was actually taken by Jennifer Yu, who's a Colorado resident. I sent her an email to see if she might want to come. I think she took this at Continental Divide. She told me this was the only time she had it just right, with the lighting, etc. And now I'm going to just flip the direction here and compare this with the large-scale instabilities that Mike Kelly was publishing, and you can see immediately, there's quite a bit of similarities, between the top side plumes, this bottom side structures, and not wanting to go the extra step, say that obviously not one-to-one was totally different plasma parameters, variations with altitude. But nevertheless, looking in other places in nature, I think, helps with our understanding and suggests that maybe something this large, just from the energy density argument, something this large maybe is driven by large-scale shear or large-scale flows, as opposed to just some little wiggles maybe that then started to grow on their own. And we also see even smaller scales. I won't go into this now, but I feel compelled to do this because when I show this to my colleagues, such as Erhan Kudecki, he says, Rob, shear is a special case. Whenever you have a differential flow between the drifts and the winds, you're going to get instabilities, and these are written a very important paper here in 2007. That's why we, even though we're thrilled with CNOPS, we really need another mission with lower altitudes and dedicated vector winds, as well as E-fields and ion drifts. Okay, this is sort of a summary of what I just told you, because I know I'm going to run out of time. I'm not going to read it, but essentially just talking about the importance of the shear in what we see in the data and how that could be very important for spread out. Now I'm going to move on to the magnetometer, show some highlights of the magnetometer. Let me make sure I got my clock here. Okay, about halfway through. We put on the magnetometer in this top panel. We had to convince the Air Force, you got to have a magnetometer. They said, what? You don't need it. We said, no, we need it for B cross B, because we wanted to get highly accurate electric fields to 0.1 millivolt per meter, and we argued even the best magnetometer models in some places can't deliver. So we put on a magnetometer, and we also used it to get B cross B to put things in locally into compute E cross B and do such other things. But the instrument, no surprise, is just a science bonanza. We're able to see DST signatures, currents, Poynting flux measurements, magnetic structures, quite a lot. I'm going to just show a few examples of the ones with these little red arrows here. This is actually a picture of Mark Kuhn, who's unfortunately no longer with us. I think this was the last magnetometer that he built that flew in. Well, that's not true. I guess Messenger or something. But anyhow, last Earth orbit. And here's the mag, and again, it was just on a 60 centimeter boom. I mean, everyone argues you've got to have 10 meters or whatever. Of course, you want a longer boom because you get the spacecraft interference is diminished. But in this case, with just 16-bit A to D, 60 centimeter boom, we're actually able to do quite a bit. Here's an example of what 1 day of CNOPS mag data looks like. The 3 components, X, Y, and Z. And when you look at it, you think, oh, isn't that the spin? Remember, we're not spinning. This is just the fact that the Earth's magnetic dipole is offset. And if you're going at a 13-degree inclination with a highly elliptical orbit, you're going to see a pattern, which is essentially one orbit. Each one of these is a single orbit. These are the 3 components. The total field of the equator, of course, is only about 30,000 nanotesla, these altitudes. The one problem we had, which we knew about ahead of time, was that the torque rods fired to keep CNOPS is pointed in the same direction throughout the orbit. We had to identify and remove those. Not a problem. And essentially, yes.
What is the limitation that you get with this only extending 60 centimeters?
Okay, it means you see a larger interference from the satellite. You want to have a long boom, so it goes over 1 over r cubed. So just being a little ways away helps. And 60 centimeters, I think, we didn't want to be body mounted. 60 centimeters was a great advantage. We would have loved to have been.
And the
2 meters
interference from the satellite you see in the data how?
Yeah. Okay, the best example is right here. These torque rods is interference. But those are there's a flag and everything. You can identify those easily. But what you can identify, and I didn't prepare a slide on this, is much smaller interference down on the nanotesla level. That's harder to nail. So again, if you could be away from it, it's less. Now actually, here's a couple of days of mag data. I had actually made this slide for another purpose, but does this still work? Yeah, okay. The 3 components, in which now we've removed the model. In this case, we use the IGRF model. And as you can see in the northward component, there's this sort of spiky residual field. Well, of course, that spiky residual field is nothing else than the DST signature. And it became immediately obvious that with a low inclination satellite, with a mag, you've got DST at every 90 minutes. You get a full, DST, which is of course done with some ground-based magnetometers. They give 1 hour averages through Kyoto and all that. It's a powerful tool. I think we all know it. In this case, we're actually able to get DST continuous, or get the signature continuously, and this is associated with the ring current. Here's actually our DST for several years on top of the Kyoto DST in red, and they track beautifully. And Guan Li actually wrote a paper published in JGR in which she was actually able to look at a lot of the asymmetries in the ring current were not available on the DST data by looking at by the CNOS mag. So that was one of the first results from the magnetometer. A second obvious one is the electrojet. Now the electrojet itself, as we all know, is a strong current, which dominates in the daytime. It's an eastward current. And in this case, we're just looking at the component parallel to beam. So we've subtracted the model field, and we're looking at the residual. And I'm plotting that this is latitude versus longitude here. So these are all little latitude, plus and minus 13 degrees, and at different local times. And it's a little hard to see, but hope you can tell that the dark blue is the strongest field, at least in this direction. And here in this time frame, 11 to 13, you see a very strong electrojet current. Now also, we're looking for reversals and things like this, but nevertheless, I think this really shows a very strong. You can even see at the other local times where it's not so washed out, you can even see how it just beautifully follows along the magnetic equator. Because the magnetic equator is horizontal, that's where the electrojet is enhanced. Now we can take all the data, this is for this one period, plotting at local time versus longitude, and you can immediately see that there is a longitude effect, which we'll attribute to the tides. This is Herman Lohr has shown this, and see this very clearly in the CNOS data. In fact, to compare, we have actually Herman's data right here, and I actually gave a talk on this at EGU for Herman Lohr's retirement, and I was able to say how the real test is how does it agree with the CHAMP data, and as you can see, it's a very, very nice agreement. So we have the electrojet data. We also have delta B's associated with the actual depletions. Now most people think, oh, they're just electrostatic. Why should there be a delta B? Well, actually, Harry Kuhn saw this first on CRESS, and Claudia Stoll and others have saw it with CHAMP data, looking at diamagnetic currents, etc. But in this case, I won't go through here, but you have the electric fields and the actual currents. The little green is actually the pointing flux. And you can actually see from this case in the northern hemisphere, the pointing flux is meridional away, in this case is meridional down, essentially following this S vector here. And so actually, if you take the delta B that we measure and the electric field that we measure, in each case you actually show the energy is polar. We also can do statistics with delta B. Well, first I just have this one example here. I'm not going to show you statistics, but I am going to show you that on some of these passes, there's a very large magnetic signature. You see here. Now, Bill Burke has written a paper about Alfvén waves, so has Potelet, and the fact that sometimes we see this strong, other times we don't, it obviously has to be related to the plasma density, but there's more to it than that. Whether these are filamentary structures, there's quite a bit of work left to be done. But the very fact that these sort of pop out at you, really, when just plotting a sonogram of the magnetic field data, I think shows that the spread F instability itself is very rich. And I know, like Rayleigh-Taylor is basically an electrostatic one. There's more going on. We can expect currents on the sides of these bubbles. And Eugene Dow actually did a thesis on this at Cornell. But as far as the data, is really relatively unmined. So the magnetometer's results here. DST gives us a new way to study the ring current. We're looking at the electrojet. I didn't show any F-region dynamo. That's a much weaker current. We're still working on those. And the AC magnetic field signatures really complete the electrodynamics of these plasma density depletions. And now I'm going to move on to the third and final part of the talk, in which I talk about the wave data. And there's so much to talk about. I've actually decided to just confine ourselves to 3 different areas where we have new results. One is from electric fields associated with lightning, power line radiation, and then Schumann resonances. Now, again, here we are in Colorado, where thunderstorms are famous, and thunderstorm research is famous. And the question is, of course, you can have your sort of sketch of a thundercloud. The question is, what goes on above the thundercloud? How much energy goes up, and how does it get there, and that sort of thing. So this is just a cartoon that we drew, showing the wave. A lot of the wavelengths should just bounce off the bottom of the ionosphere and come right back. But the reality is, quite a bit actually goes through. And I know, again, my advisor, Mike Kelly, flew some rockets at Wallops to show this, and others have shown it as well. That it's not just the high frequencies, but the low frequencies that seem to penetrate. Now, so here's the CNOS measurement region up here. So to the first order, if you had a very large plasma density shelf here, you would expect all the waves, the very low frequency waves, to just reflect. But that's really not the case. Here's a 25 seconds, I think this is from our burst data, of electric field sonogram. Here's actually the raw data. And here's from the lightning detector. This is, remember I mentioned that Bob Holsworth provided this, and we integrated it into our experiment. So here are the actual flashes, and what you see is that there's quite a bit of low frequency data right with the associated with the actual lightning flash. If you know the lightning flashing, you can calculate the speed of light. There's a slight delay, but basically you're right over the storm, and that's right where you see these low frequencies. The higher frequencies go a little faster, so you see there is dispersion. But nevertheless, you see even at these high altitudes, 828 kilometers, you see associated with the lightning flash, the low frequency waves. Here's some lower hybrid waves right there. Here's a transmitter right there. So the idea is, we're seeing this. So direct measurements, again, right over the flash or the thunderstorm cell, is at these high altitudes. At the equator, where the magnetic field line is horizontal, it's not at an angle where it can help propagate, was a somewhat of a surprise. Another aspect of the lightning data, the VLF data associated with lightning, is that you get a lot of what's called instabilities and lower hybrid instabilities in particular. And here, for the first time, because we have a 3-axis measurement, 3 20-meter tip-to-tip booms, we can actually take burst data of all 3 components, and that's shown here, and then we can rotate it into magnetic field aligned coordinates. And you don't normally expect parallel electric fields at low latitudes. I'm looking at Bill there. Usually there's a high latitude, something associated with the aurora, but here actually the lower hybrid instability will actually predict a strong parallel component, and we actually see that right here. So this is just another example of some of the new wave activity from CNOS. Now, here's just our lightning detector, just to show you it seemed to work very well, mapping with other, in this case, agreeing quite nicely with the Marshall lightning detector. Okay, now I'm going to move on to the 50, 60 hertz power line radiation. And I should point out, well, if we're seeing all these low frequency waves from lightning, maybe we should see the power line radiation. And when I was a grad student, this was a hot topic. This is back in the 70s, from the Stanford group, and they were arguing, could the radiation actually affect the radiation belts, and could there be a Sunday effect where on Sundays where you don't use so much power line, might you see that in the data? And people always look at higher, people had filter banks where they were looking at higher frequencies, harmonics. And I kept saying, well, ever since I was a graduate, I said, well, why don't we just measure it? But to do that, you need the broadband data at low frequencies. Well, we have that on CNOS, and we have that actually because we wanted the irregularities, get the low frequencies. In this case here, we have broadband data at 500 samples a second. So I'm just plotting a sonogram made on the ground of data from 0 to 80 hertz at night. And here you can see there's 60 hertz in Brazil, right over Brazil. Here's 50 hertz from India, right over India. So again, the low frequency electromagnetic wave is penetrating directly straight up. It's not bouncing around in the cavity and just dissolving or some getting to the satellite via some other path. Rather, it's coming directly. And this is I believe, a surprise. Since we did this, the Demeter group has also seen it, although they don't have the waveforms. But nevertheless, this is good. I mean, we're all seeing it. And it's really, I think, making us sort of rethink the whole idea of the ionosphere waveguide and rethink how does these very low frequency electromagnetic waves penetrate into the ionosphere. Here's another one. There's 60 hertz over Brazil. I should point out, Brazil has 60 hertz, India has 50. It made it very nice for convincing us we were measuring. And that's mostly at night. Here's some daytime. Why is it mostly at night? Because the index of refraction is such that, you know, you want lower plasma density for the waves to, they sort of couple more efficiently. But you can see it in the daytime as shown here. We then took all the data. We made some maps of distributions. Again, just looking at the nighttime data from this about 1 year period. And you can see very strong. Here's the magnetic equator, plus or minus 30. Just bend everything together because we had to eliminate the hissing in the background. It's a little challenging. But nevertheless, you can see the very strong Brazil and India sectors and some of the African communities as well. In fact, if you look at a map of where's the distribution, then you can go back and try to, I've been trying to look for, you know, a little 60 hertz here in Africa, you know, what's the source of that? But basically, though, I think this is sort of a new result from an old question about the actual power line. Of course, does get into the ionosphere and amplitudes that we can measure. And Bill Farrell and I are working on getting this result out. Should also point out that we see higher amplitudes at the higher altitudes. And you might think, why? You know, isn't the power line, shouldn't it be strongest right at the bottom? Well, just want to point out that we're only measuring the electric component. We really need a search coil to measure both E and B. And essentially, they vary inversely with the plasma density. So if we had had a search coil where the amplitude of the electric signal gets smaller, where the plasma density gets higher, the amplitude of the magnetic signal would have gotten higher. That's what we predicted if we had had that measurement. Okay, now finally, I want to talk a little bit about Schumann resonances, and then we'll wrap it up. Now, Schumann resonances, I don't know how many of you have studied Schumann resonances, but they essentially were predicted in 1952 by Schumann. No surprise there. And saying that we have a spherical cavity here, and that this waveguide would have some resonant modes. And he worked out the expression for that, and which is shown here. And it would depend on the radius of the Earth. And essentially, these are how the modes are actually predicted. So, you know, you can actually just calculate them, and you'll see the first one would be at 7.8 hertz, 14 hertz, 28, 21, 28 hertz, etc. So they're not, you don't want to refer to them as harmonics, because they're not harmonics. They're simply the higher order modes associated with this cavity. Now, there's been all this work done with Schumann resonances on the ground. And there's cottage industry societies, you know, they work on it. And here's some examples of some ground-based measurements. In fact, NASA even dug this out, actually had a pamphlet on how to set up your own antenna if you want to look at Schumann resonances. Maybe some of you in the room have this in your backyard. But here's some data from a ground-based 6 hours of data. You see the different modes. And here's some of the modes sketched here. And they were first observed on the ground and reported in Nature by Balser and Wagner in 1960. And they're very powerful. They address the global electric circuit. They address tropospheric weather because you can see how these vary with the weather systems. You can look at space weather effects because they would affect the ionosphere waveguide. And one of my colleagues even thinks they're important for climate change, and I'm sure he's right. So what about space? Could you see these in space? Well, here's our data. This is the 512 sample per second broadband data, in which we've actually created these sonograms on the ground. In this case, I'm putting 2 orbits next to each other. So here's the nighttime, daytime, nighttime. Here's the phenomenon called ELF hiss, which I'm not even going to talk about. And lo and behold, here are the Schumann resonances right here. And I must tell you, without going any further, that my postdoc, Fernando Simões, who had worked in France with Bertillier's group, he came as a postdoc and he found these. And I almost feel like this was his mission. He had to find these. And for a long time, he didn't have a computer, not a long time, but for a few days. When he arrived, you know, NASA in its wisdom doesn't give foreigners a computer account right away. So he's busy looking with a magnifying glass at some sonograms that we had. And I kept saying, Fernando, blow them up, blow them up. He said, I don't have a computer account. And anyhow, he got the account, of course, working. First thing he did was he blew these up, and he saw the Schumann resonances. And he had actually done some research in Europe on them, and it was really a great moment in our group when he he proudly announced them. Here's a sort of a blow up, and here they are. Here's the HIS. Again, here's the Schumann Resonance. Well, we actually published a GRL paper on this. It was my only time of trying to get a paper into Nature and failed, but really felt this was very significant and important. And we tried science, and then we went to GRL and went on with life, so to speak. But nevertheless, we have 20-meter tip-to-tip booms, with high accuracy ADDs and all this. So we're actually, I think, able to see up to 12 resonances detected. And yet they're about 1,000 times weaker than what you see on the ground. And Fernando is very keen on emphasizing that other planets may have Schumann resonances, and this is a good way to, study them remotely. So why not? Study the ionosphere cavities and things like this. These are some figures from the GRL. This is from, I guess, Mansion. And as you can see, the many different higher order modes. Now, there's actually a more accurate approximation. This is what Schumann published in '52, and you can actually see how the actual modes themselves depend on, the dielectric and quite a bit of the actual properties of the waveguide. And so we've actually been studying these as a function, for different situations, trying to extract that data. Here's actually Schumann resonances for 3.75 years of the program, in which my colleague Herman Freudenreich and Fernando have been extracting the background. And so actually what you're looking at is frequency here versus time. So this is, again, 3.75 years. I put the EUV here. And you can actually see, here's the integrated power, so to speak, of the Schumann resonances. Here's actually the 50 and 60 hertz that I talked about earlier. And actually here are the different modes. Now you might say, why does it get strong here? Why does it get strong? It's actually complicated because we have an elliptical orbit. It depends on, as perigee goes through the night side every 2 months, there are some various factors are beating. And just to remind you that the plasma density is the key thing. I mean, we'd love to say, this is due to a solar effect or climate change or whatever, but we really feel the modulation can be explained in first order by the actual satellite harmonics or satellite orbit and the periodicity and, of course, the plasma density exchange. With a circular orbit, you wouldn't have that problem.
So, but that in a way is an advantage. If this model for the Schumann resonances has all the right parameters in it, you should be able to deduce the actual altitude of the satellite.
Yeah, that's a great point. Yeah, thank you. Yeah, we'll use that to our advantage. Yeah. And if it didn't show that, we'd be worried.
It's a nice check of your elliptical orbit.
Yeah, I should put the orbit on it. Thank you for that point. It's and also you can see how the 50 and 60 hertz changes in the same way. Okay, so I'm about done here. I just wanted to show this is, of course, the ionosphere slide that I showed at the very beginning. I don't know whether you can see this, but the idea here is from the lightning and from the 50 and 60 hertz power line radiation and from the Schumann resonances, we feel we really need to sort of rethink the Earth ionosphere waveguide. Here I kind of drew some waves that are captured. Here are some waves that kind of escape. Here, the Schumann resonances we know have to be a resonance or they wouldn't, you wouldn't have anything to look at. So that has to sort of fill the waveguide. But nevertheless, the fact that if you can have a storm and a Schumann resonance associated with it is something which we're looking into. So I guess my final wrap up here on the ACE fields. We saw upward propagating electromagnetic radiation from lightning, the power line, and the resonances. These really come as a surprise, particularly the Schumann resonances, which are really just confined to that waveguide, or they wouldn't be resonances. So the Earth's atmosphere is leaky, and perhaps some modelers, particularly electromagnetic experts, might start thinking about that. And I don't think that itself is news, but I think this data really shows it's maybe leakier than we thought. So some new model of ELF propagation we think is needed. The data suggests that the Schumann resonance could be important in the environments of other planets. And just to end here, I think VP's extensive database promises to expose many new processes to capture our attention for years to come. Thank you. Question? Yeah, Mark.
Question with the Schumann resonances.
Yeah.
So they're a low frequency type of wave
Right.
that has a relatively long
Wavelength.
wavelength.
Think of the circumference of the Earth. Yeah.
And in the ionosphere, it would not be propagating. It would be an exponential decay. I'm just wondering.
Yeah, you're thinking about the K
you get
vector.
some
Yeah.
of it tunneling through, and I'm just wondering,
Yeah.
has anybody calculated the amplitudes that you're seeing? Are they consistent with just a simple?
And that's a good question. I should ask Fernando. I think, yeah, I should. You're right. It is more of it's not the regular wave with a K vector. Yeah.
Yeah.
Yeah. Thanks for that point. I think having the amplitudes is besides seeing them. There's the next step. All of these take sort of like a thesis and this and that. We welcome input and Fernando's gone back to Europe, but the data's he's still interested. I'm just saying it's a big project, but we're working on this. Yes.
So the instabilities you're talking about you were just looking at the hydrodynamic case, right? So I'm just wondering if you include the magnetic field variation in the analysis, which you show that you have waves generated, is that going to stabilize the instability or give it even lower growth rate?
I don't know. I see. Okay, great question. Let's just go back to these guys. Here's what you're asking about.
Yeah.
I don't know is the answer. But my thinking, and also looking at CHAMP data, is that this is a delta B which is really static. I mean, it's sort of along the walls of the depletions and stuff. Now, why they're suddenly stronger here than not here, I don't know. Maybe the drivers, the E fields, presumably are stronger here. But it's like the static current structures, like filamentary currents that you see in the auroral zone. Satellite flies through them, it records a delta B. Your questions are good. I don't know how to answer that, but it needs to be factored in. As I said, we're sort of completing the electrodynamic picture, so to speak. But that's a good point.
I'm just wondering if that has anything to do with because the ionosphere is not exactly a ideal fluid, right? It has all things going on, and then the magnetic field is so large, and maybe it doesn't matter. I don't know, because you got.
Okay, well, let me just emphasize. These are tiny. Okay, the magnetic field is 30,000 nanotesla. So these are on the order of 5 nanotesla.
So that's a really.
That's still the magnetic field is, believe me, it's there to stay, and it structures everything. The regular magnetic field. So these are like little fuzz. Yeah.
Okay.
Yeah.
I have a quick question. So, what is sensitivity of magnetometer on
CNOS?
On the CNOS? Yeah.
Okay,
how
great.
good
It's about a nanotesla. Now, with averaging, we can get somewhat better than that because we oversample. But the LSB, least significant bit, is about 1 nanotesla. Because we knew it was a low inclination, instead of making it a 60,000 nanotesla mag as Mario might normally, I said, let's make it 45,000 because we're at the equator. So you pick up a little sensitivity there.
Right. Yeah. I wonder if people who doing Earth main magnetic field modeling are they interested in CNOS?
Oh, thanks for asking. That's great. Where's Stefan Maus?
Yeah.
We've been working with Stefan and with Herman, of course, to get the chaos model. And
POM.
And POM, I'm sorry, yes, POM and chaos. POM.
Yeah.
That POM really changed our lives because we were using IGRF and the AFRL was giving IGRF with the data, when they sent you the data, and we were just saying, so this is not good enough. So POM really, thanks to Herman, the POM model really sort of helped us with the offsets considerably. And again, we were 7.5 years when CHAMP was still up, but now, of course, Swarm. And now we're using chaos. And IGRF isn't bad, though. I mean, you can work that. You have to remove the DST in this thing. But I will say, much to my delight, the fact that Herman has taken an interest in CNOS with its little 60-centimeter boom has warmed my heart. And although we don't have a scalar, it's not CHAMP, it's not Swarm, but I think it can make a contribution.
Yeah. Okay. Thank you.
Yeah, what I find intriguing about that is that you, with this tiny magnetometer, can make meaningful measurements. Does that mean that for the next Jupiter probe or so, we don't need these gigantic beams?
Well, Farby, I'm going to take the credit on that. I think a lot of magnetometry people are ready to shoot me for saying this. You still get higher quality data with the longer mag, no question. And keep in mind, when you go to Jupiter, the field strength changes by, you need almost many different gain states and this and that. Here we're able to do the whole thing in one single gain state. But I think the bottom line, I remember when Ionosphere put the mission to Pluto, and I said, where's the magnetometer? He said, we couldn't afford the boom. Pardon me?
That's what I said.
And he said couldn't afford the, I said, just body mount, just put one on at least to, see some, or, put it off 10 centimeters. But, he was proud of saying that, what are the saying, an enemy of good or something, is whatever. Just say, no, Rob, I've got my mission, and so be it. But, we're proud of the mag data. We wanted a longer boom ourselves, and a long boom helps, but here's what I'm not showing you all the interference we had to subtract. Maybe that's the better answer. But no, we were happy with it. I think Mario built a nice mag.
I wanted to make another comment to what Art said, if I may. So with the Schumann resonances and this kind of a detection, that is very analogous to solar seismology, where the 5-minute oscillations we detect also in a region where the actual waves are evanescent, which is the cool solar atmosphere. And we just measure that tail. So that's no obstacle to learn meaningful things.
Thanks for that comment. I'll think about that. Yeah, I think it really is open. Like it's an area that I personally was not involved in, but it really gets you thinking about really geophysical data.
Then the other question I have is, all in all, everything one was always trying to visualize how sort of the whole 3D multi-dimensional picture of the ionosphere looks like with these kind of measurements becomes very real, it's almost like out of a 3D printer. Now, is there a need for operational monitoring, this kind of stuff?
Okay.
Because that would, after a research mission, would be
the next step. In fact, CNOS was supposed to have follow-ons and all this. And there actually is a follow-on called Cosmic 2 that's going to doesn't have electric field probes or magnetometers, but it's going to be looking at the plasma density and the ion drifts. I think one advantage of having the low inclination is every orbit goes over all the longitudes. Where for your polar orbit, you have to wait. You're not going to go over all longitudes.
Yeah.
So I think that helps with getting sort of the picture. I'd love for there to be a follow-on. I can get you to write a testimonial, but I think it's. I think there's still so much more, not only with these data, but so much more that could be learned with a satellite with propulsion, where we could really go even lower. I mean, you can imagine the ELF phenomenon below the F peak, if that got stronger and that sort of thing. Because all of these measurements were essentially about. Yes, go.
Oh, you mentioned that the wind shear, the zonal wind shear, is the main cause of the plasma irregularity. So what causes the wind shear in the first place?
Great question. I'm going to tell you, Art Richmond can answer that. I guess it has to do with the conductivity and the winds. The non-local distribution is a function of longitude and latitude.
Well, it's just in the evening in the low latitudes, you have this strong dayside pressure bulge that's accelerating the wind toward the east. When you go down lower, that pressure difference gets much weaker. And normally during the day you have a westward wind, so it doesn't reverse. You just end up getting a shear.
Yeah. I think we talked about coming to Mecca here. I think this morning, this discussion I had with Art about this made my whole trip worthwhile. But I think the actual why you have the shear is something we're not addressing. I wish we'd measure the neutral winds. That's the key thing we're not measuring. But I was pleased to know that Art has been working on it and has a paper on it.
What is the scale of shears? Like that's responsible, or what is the spatial scales?
Spatial. Okay. Look here. Here's the here's like a continent, you might say. So here's this region. It goes in clumps, not just the instantaneous region. Here, and this is where the entire ionosphere was elevated due to the zonal eastward field that made it go up. And as you can see, when the satellite went below the elevated ionosphere, we see the large shear. In other words, this is the direction of the zonal field has changed. So, here's, you get a sense, but this is over a wider area. It's not just a little bit. But basically, it's, just to go back to this one, you can see here that a couple hours of local time. And then when you have this sort of elevated ionosphere, that's where you're seeing the shear.
Thank you.
Yes.
Oh, I actually have the same question. I was just wondering that during the irregularity times, how bigger are the wind shears compared to normal?
Well, normal is there's really usually you don't see any shear.
Is that because it doesn't exist, or you don't get to the altitude out there?
Yeah, great question. I'd say we don't get to the altitude. We got to be at sunset. You got to be at the right time. Now, I bet if you're in the certain seasons and certain longitudes, maybe there's still no shear. Maybe, But I'm just saying that the times whenever we saw the ionosphere rise above us, we see the shear. I mean, there's maybe a few exceptions. And I do have a few orbits where we went below, really later in local time, not at sunset. And of course, I immediately looked for the shear. I didn't see it, but it wasn't sunset. It'd be like at 2 in the morning. And we just went below the FP, just later in the mission when we started getting lower. So I was able to test that.
Thanks.
Yeah. Okay.
All right, if there are no more questions, we thank Rob again.
Okay.